question number 10. Yeah, this one, yeah, because this one is a concept understanding. Some students, got confused, yeah, because here we compare the algorithm's efficiency, performance, well or not, when the problem size is relatively small. That one. Okay. Yeah. The first question I'd like to clarify based on intuition. Yeah. Intuition. Yeah. Many students may have this intuition. Okay. Yeah. May have this intuition. So their logic, reasoning, or intuition, or common sense, whatever, may look like this. Okay, yeah. Yeah, let me just write the meaning in a short way. Yeah, so here, in this way, the faster algorithms are likely faster, yeah, for smaller problem sizes. Okay, likely, all right? All right, yeah, that's the intuition. Think about it. So do you believe this or not, right? Yeah, think about that. Or at least it comes from some natural understanding, right? Yeah. Okay, yeah. But I like to clarify things, with a little more background to help you answer this question. Okay, likely, this word, yeah, not quite rigorous, right? Yeah, likely, yeah. There could be some exception, right? Although you say likely, but still you allow exceptions, right? Yeah. But here I like to point out another important fact in our real world programming. Okay, yeah. So that's this. You will have this kind of experience more and more later. So that is, in order to get a faster algorithm, we may, yeah, here I just, use this word may, we may spend more time to do preparation. To do preparation. Okay, yeah. This part, many times we call overhead. Overhead part. You need to spend time to do preparation. Yeah. Because the faster algorithms are not free, right? The effort, you need to pay more effort to get a faster algorithms. Okay, so some of the effort is reflected in this preparation part. And sometimes we just call, overhead. Okay, overhead part. Spend more time to do preparation as the overhead part. Okay. And as a result, as a consequence, and the performance gain from the smaller problem sizes may not be able to overcome the overhead. Okay. You may have some performance gain, yeah, but for smaller problem sizes, even you have some performance gain, that's relatively small, right? Yeah. Okay. Yeah. That small gain, think about this, that small gain cannot overcome the overhead part. Think about that. Okay. Yeah. But for larger problem sizes, then because your gain is huge, think about that. Your gain is huge, but the overhead part is not that big. The overhead part usually fixed. The overhead part, you do preparation, that cost is fixed. Fixed, that means when you increase the problem sizes, that overhead part is not increased. Yeah, you pretty much use the same amount of preparation time. Yeah. Then your huge gain can overcome the overhead part. Think about that. That, behavior, okay, typical behavior, right? Yeah. So this is, let me call the overhead view. Okay. Yeah. We understand this question with this overhead view. Yeah. But I also like to give you another view. Yeah. Another from asymptotic. Yeah. Let me write the correct spelling. Asymptotic notation view. Yeah. From asymptotic notation view, we can also see this point. Now, here I do not write the whole definition, but because it would take too long. It's not necessary to write a whole definition. Yeah. Here I just write the related relevant part. I just write the relevant part, related to this question. The relevant part. So here, let's look at the big theta notation. Okay, yeah, big theta notation. Yeah, the relevant part. Remember we need to find the C1, C2, two positive constant, C2 for the lower bound. Yeah, so here, when we describe this asymptotic notation, we can find positive C2 constant, C2 multiple of G of n greater or equal to F of n, less than or equal to F, and less than or equal to C1 multiple of G of n, okay? Then, after that, there is another important condition. For all n greater or equal to m of 0, m of a 0, okay? Yeah, yeah. this number and 0. And I explained it corresponds to when m is sufficiently large. Remember that? Sufficiently large. Okay? So why we have this condition? This condition tells us we can skip relatively small sizes. How about that? This exactly tells us skip some small, or precisely relatively, right? Small problem sizes, right? Okay, yeah. Why skip? Because not important, okay? When the problem sizes are relatively small, when you do comparisons, the better, worse behavior won't reflect the cases when the problem sizes are large, and we want to focus on the large problem sizes, but not relatively small problem sizes. That's the meaning from asymptotic notation point of view. Okay? Yeah. The reason we get scared because, yeah, so here, let me just give you a few more reasons. Because too much distortion for small problem sizes. Okay, so here, distortion away from your formula, right? Because think about, the overhead part will make the distortion. Think about that. The overhead part will make the distortion. Okay, yeah. So your formula, your efficiency formula, your performance formula will be distorted by certain overhead, the overhead part for smaller problem sizes. That's the reason. Think about that. Okay? Think about that. Yeah. Here I give you two views. Yeah. Two closely related views. Okay? Yeah. So with this understanding, then you can answer that question better. Yeah. Okay? Yeah. So that's the necessary information you need to answer this question correctly. Okay. All right. So let me complete the hints part right here.